In the last video, we have seen how to construct a Maromori function with poles exactly at the given points. So now the next question, can we construct an analytic function with zeros exactly at the given points? So what was the idea in the construction of Maromori function? So we were taking all the given poles and we were subtracting the singular parts from the function, okay, then making it analytic. So here what happens, the zeros are given. So naturally, so if you want to construct a function with zeros exactly at z1 and z2, the natural choice is z minus z1 into z minus z2. So, but we will be dealing with infinitely many points. So naturally what we need is the notion of infinite products. So that's what we will discuss in this video. So now we will develop the basic preliminaries regarding infinite products, and next we will move to the construction of analytic functions. So here is the definition of convergence of an infinite product. So naturally it is just like similar to the convergence of infinite series. So it is P1, P2, etc. goes on. So this is denoted by this notation. Now this is evaluated as P equal to limit Pn. What you do, you take all the finite products and take the limit. But we will have a crucial assumption. We assume that the limit is not non-zero, because if we allow P to be zero, then the points means zero. If there are some zeros here, then if some of the terms are zero, then the whole product will be zero. So because of that, we will not allow zero to be the limit. Okay, that is one thing. Another thing, this tells you that all the terms should be non-zero, right? Because P should not be zero. But what happens is that if there are finitely many zeros, that we can exclude and we can reformulate this partial product and do. That's also allowed. An important thing is that just as in the case of series, if it's a necessary condition, if an infinite product converges, then the nth term will go to 1. That's very easy. You can just take the quotient and find the limit. Now this is similar to the fact where if nth term of a convergent series goes to 0. So now, because of this reason, we will have a convention like this. We will consider always product 1 plus an with an tends to 0. So this is only a convention. Okay. Now here is a very important theorem. The convergence of the infinite product n equal to 1 to infinity 1 plus an with each 1 plus an non-zero. The convergence is equivalent to the convergence of the series with the nth term log 1 plus an. So here we are taking the principal branch of the logarithm for each term. Okay. So this is the necessary and sufficient condition. The importance is that the convergence of a product, the question is now converted to the much familiar question of convergence of a series. Now we prove it very easily. So first you assume that the series is convergent. You take the nth term, it is Sn, denoted by Sn. So it converges to some S, say. Now you take exponential. So e power Sn, e power summation of this, that becomes the nth partial product, Pn. So since e power Sn converges to some S, e power Sn by continuity of exponential, it will converge to some e power S. And that is what is P, which is exponential power S, therefore it is non-zero. So hence Pn converges to P and it is non-zero. So this is easy, one side is easy. Now for the converse part, you assume that the product converges. Okay, that is Pn converges to P, which is non-zero. Now Pn is this product, the nth partial product. Now Pn by P converges to 1. Now Pn by P converges to 1 means it comes in this disk around 1. Therefore it comes into the principal branch of the logarithm. Therefore you can apply the continuity of principal logarithm. So then what happens? Yeah, then by continuity log Pn by P converges to log 1, which is 0. Now we use continuity because it is log. Now what happened? Now a simple computation, log Pn by P will be log Pn minus log P plus some multiple of 2 pi, integer multiple of 2 pi I. So now it's simple computation. You just write it like this. Now what happens is that you compute hn plus 1 minus hn into 2 pi I. Again, simple computation. This is an imaginary part of this thing. So you equate the imaginary, compare the imaginary parts. So we will get argument Pn by plus 1 by P minus argument. It is a principal argument. Pn by P minus argument 1 plus An. Now what happens is that this goes to 0 because both quantity goes to 1. Therefore, the first two terms goes to 0, and the third term is a principal argument. Therefore, its absolute value should be less than or equal to pi. So what happens on the right hand side? You will have something, some pi plus some small quantity only. So what happens is for large n, the left hand side should be less than or equal to pi, or maybe some small quantity. So what happens that this absolute value of hn plus 1 minus hn should be 1 by 2 plus some quantity, small quantity. That means this has to be a constant sequence for large n. So that what happens is that hn plus 1 should be hn. That means you have a, so you apply that here, and so you apply it here. So in the previous slide you have this, hn comes here. So what happens that you have this hn here. So this is a quantity h. Okay. So what happens that as n tends to infinity, this quantity goes to 0, which already we observed. This quantity is Sn, so that converts to this quantity. That's what we obtain. This plus this. So that's what we obtained here. Sn converts to log p minus h into 2 pi. Hence we obtained the proof. Now another result of the same nature, that is the convergence of an infinite product is the absolute convergence is equivalent to the absolute convergence of this series. So that's again very easy, because if this product converges, we know that an tends to 0. If the series converges, then also we know that log of this goes to 0. That means log 1 plus an goes to 0. So in both cases, what happens? So in this case also an goes to 0. So whatever we assume, either the absolute convergence of the series or the absolute convergence of the product, an will go to 0. Okay. Now what happens? You use the fact that limit z tends to 0 log 1 plus z by z is 1. So that's easy to obtain. So for epsilon greater than 0, there exists a delta such that this difference is less than epsilon whenever mod z less than delta. Now since an tends to 0, for this delta there is an n epsilon such that mod n less than delta whenever n is large. Now since mod n less than delta, n greater than n epsilon implies this. So from here, putting z equal to an, log 1 plus an by an minus 1 less than epsilon. Now it's a simple triangle inequality and other small estimates. You will obtain finally two inequalities. That means 1 minus epsilon into mod an less than or equal to mod log plus 1 by an, log of 1 plus an less than or equal to 1 plus epsilon into mod an. Now this you can see that, so this series, if this series converges, then this series will converge. Series with this term will converge, and if this series converges, then so that's an if and only if thing. So these two series converges simultaneously. Now I have posed a problem here. Absolute convergence is very important. If you don't have absolute convergence, it need not imply anyway. So summation n may converge, but product 1 plus n diverge, and otherwise also have. Now using these results, we can obtain an infinite product representation like this. So product, so this is something you can compute. So I have given enough hints here in this couple of problems. You have so the third problem I did not give a hint. We'll discuss in the tutorial session. Okay. So with these preliminaries, in the next lecture we will go to the very important results, again due to Weierstrass, something known as Weierstrass product theorem and all. So which will give you a kind of this will give you an analytic function with zeros at the prescribed points. Okay, see you.